Today we're going to do some actual control design using root locus as a core technique. Over here, I have an example that I asked you to think about it. Suppose I have an open loop system, given have a pole zero map like this. You can draw the root locus and understand if this open loop system is put into simple feedback control, P control, proportional control. The root locus is going to be like this. It has 3 poles, so you can calculate the asymptote, angles, and centroid. The centroid is going to be the geometric center of these 3 poles. There are no finite zeros. This is -1, -2, -5. So the average is going to be 5 plus 2 plus 1, 8 divided by 3. It's going to be roughly, I would say, a little bit about here. And then the asymptotic angles will be 180 degrees plus minus over the number of denominators, the order of the denominator minus the order of the numerator, so it's 3 minus 0. So it's going to be 60 degrees, something like this. And then there will be a, so this 2k plus 1, there are 3 asymptotes. So this root, the branch starting from here is going to go to the left, and then the branch starting from these 2 will go to the middle first, and then to the infinity. And then this is k increasing k, capital K, the gain of the feedback loop. This is small k, capital gain k from 0 to infinity. So what you can see is this is a less dominant pole for the closed loop system. As the pole evolves from here to the left, this is less dominant. The more dominant poles are here on these 2 branches. Now, the root locus is showing that we're going to have complex poles, closed loop poles, and we can correspond the time domain responses of a complex pole like this over here to the time domain responses, right? We already cleared that this is less dominant. So the dominant system behavior is going to be like a second order system. And the relationship of the time domain responses, as we recall from second order system analysis, is going to be dependent. So the time domain response is going to be dependent upon the system parameters. And specifically, it's going to depend on the damping ratio, zeta, and natural frequency, omega n. Now, the damping ratio story is as follows. If we have a pole, a pair of complex poles, for this system, suppose the poles are located like this, then the root location is, this is the poles of the system is, so the system poles is, just solve the polynomial, the roots of the denominator polynomial is negative zeta omega n plus minus square root 1 minus zeta square omega n j. That's the pole locations. So specifically, that means this is negative zeta omega n over here, and then the not axis. Imaginary component here is square root 1 minus zeta square omega n. So that's how location of poles are related to the system time domain behavior. More specifically, you can see that the tangent of this angle, let's call it theta. So the angle of the pole corresponding to the origin actually indicates, you can see, you can calculate, right? The tangent of this angle is this distance, this length, divided by this length. So it's going to be this divided by zeta. So now you know, for example, right here, if you have a desired damping ratio, if you know your zeta, then you can know roughly where your dominant closed loop pole should be located at in this polar coordinate, this angle you would know. So in other words, over here, if you have a target zeta value, you have a target theta value. Then you can draw, let's say, suppose this is your target theta value. Suppose this is your target. Then you can design your gain for this example. You can design your gain such that, for example, it will have this specific damping ratio for you. All right? Now, this is nice in a way. We know that we can design the closed loop, for example, to have stability, right? It doesn't go to the right-hand side of the complex plane. And we know it's an approximate second-order response. Now, let's see, using root locus technique, if you design, I have two designs over here, you add a 0 to the system. This 0 is exactly located at the pole location. This 0 is a little bit to the left. Then the root locus is going to become, so you can do it again, right? For this system, the root locus, you can again calculate the centroid and the asymptotic angles. The centroid of this one is what? It's here in the middle. And the asymptotic angles will be plus minus 80 divided by 3 minus 1. So it's going to be 90 degrees. This is your new root locus. And if you think about it now, you can still have a design such that you have a desired damping ratio, zeta. So you can still have this target damping angle theta. But what happened is that your location of the closed loop pole, let me draw it here using a different color. This is the location of the closed loop pole if you use this particular design of damping ratio. The location of these is, compared with this, is much more to the left, right? You shifted the root locus to be sitting over here. So if a closed loop pole is to the left, it's further more to the left, what does that mean? Better stability, and the transient will be faster, right? The transient response depends entirely on, so the transient response, for example, the settling time depends on 4 over zeta omega n. So zeta omega n is this distance. It's the real part of the closed loop pole. If this is much more to the left, that means larger. This is smaller. So effectively, using this design, you can make the transient to be much faster. So let's see what else benefit can we have. Another benefit is the peak time. The peak time depends on pi over this damped natural frequency. So this damped natural frequency is actually this part. So the imaginary part of your closed loop complex pole will dominate the peak time. So that means if your pole is here compared to this one, you have faster transient, faster peak time. So what doesn't change? If you have the same damping ratio, let's look at here. If you have the same damping ratio, that means your percentage overshoot, which depends entirely on the damping ratio, doesn't depend on natural frequency. Your overshoot will remain exactly the same for these two designs because the angle is the same. So this design, effectively, we're going to have faster transient, which means settling time and peak time both reduce, as well as same percentage overshoot. So that's how, just adding a 0 using root locus, you will know these benefits immediately. Let's reinforce the understanding and observation using a second example. If this is like this, if your 0 is added a little bit more to the left, let's see what happens. Again, the asymptote angles and the centroid will be, we still have the asymptotic angle is still 90 degrees. It's this one divided by 3 minus 1, so it's still 90 degrees. The center location is going to be, so this is -1, -2, -5. Let's say this is designed to be -3. So the centroid location is going to be the summation of all the poles minus the summation of all the open loop zeros divided by n minus m. That means for this system, it's going to be -8 minus -3. So it's -8 plus 3 divided by 3 minus 1 That's roughly negative 2.5. So it's here. And then the angles are plus minus 90 degrees. So the root locus for this one will be like this. Again, you can design, for example, I want the same kind of percentage overshoot. So I want the same design angle. I will draw this line, which will have the desired theta. And then I can find the intersection point. This is my desired closed loop pole. There will be another one in the bottom. I will just draw this part. You can finish the remaining part. Right? So you can have your closed loop design to be like this, which compared to this one, it's still better. I'll answer a question in a minute. Compared to this one, it's still better, right? Your system, the closed loop pole is further to the left compared to this one. And then it will slightly, I draw it not to scale, but you can compare the location of these poles. You will see that the poles of this one is slightly to the right compared to this one. It's not as fast as this design. But it's still better than this one, original one. All right? So now you see the major concept of root locus design. The key observation is this. So observation is adding these stable zeros improves the transient. Just a simple addition of the zeros with a combination of what we learned previously, all the important concepts about second-order systems, can improve the transient while still maintaining the percentage overshoot, etc. This is called a proportional, it's called zeros is called adding derivatives. So because adding zeros will add, so S corresponds to taking derivative actions in the time domain. So if you have an input like this, here I just to focus on the zeros. You can see the output will have a derivative, will be adding the derivative portion of the input in it. So think about the concept over here. If the input is going up, right? If the input is increasing, what's the derivative going to be? Positive, right? So that means if the input is increasing, you add a derivative term, you're going to accelerate the increase because it has a positive slope, right? So that's why this is adding zeros to improve the transient, behind the logic adding some derivative terms in the time domain. This is called PD design, proportional derivative design. Now let's dive into a specific example. Now this time I'm going to give you even more, let's work on even more requirements. Suppose we're given, good. So let's work on an exercise. I have g of s is s plus 4 and 6. I want you to design such that the percentage overshoot will be less than or equal to 16%. So percentage overshoot is less than 16%. And then settling time, but to reduce, to decrease by 4 folds. So that's my design problem. This is saying originally I have a simple design. This is original, and I can have my root locus. So originally I can choose my gain, K, to have some stable system with some percentage overshoot and settling time. The root locus for this one is going to be, so this is 0 and negative 4 and negative 6. The asymptote angles are, it's exactly the same as this. So it's 60 degrees plus minus and 180. The center location, the centroid is going to be 10 divided by 3. That's roughly about here. Let's say here. All right, so no matter how you choose k, your design space is very small, is very limited. You can have some percentage overshoot. Let's say a 16% overshoot is somewhere around here. So if you have a percentage overshoot of 16, that means your close to poles will be here and here. So the settling time, you can conceptually understand the settling time will be rather limited. What I want is to translate the system design such that the settling time reduced by 4 times means that I want my close to poles to be further to the left. And having a percentage overshoot of 16, that means I want it to be still along this line, this angle. So we want, let me use blue. So that's the design space we're going to have. So we're going to need to come up with some closed-loop design to make the root locus to go to here. So think about scenarios over here. We need to design the system such that the root locus will go to the left compared to this one. And adding zeros seem to be the way, right? So that's the general concept. Now let's look into some of the details. First is, let's be more systematic. Let's translate this to zeta. If I know my percentage overshoot, that means my zeta from that equation on the left can be calculated. I did it for you. It's going to be about 0.504. And then having a zeta means, make sure the screen is captured, still captured. So if we know zeta, now let's work on what should zeta angle be. So I have rather small space over here, so I will draw zeta angle instead. Knowing this is the same as knowing that. So you can calculate using this formula. So you know that, let me call this theta tilde. I know that this angle, 180 degrees minus theta tilde, is going to be inverse tangent of this damping ratio division. And now we know this data already, so we can calculate this. And then we can eventually calculate theta tilde. The angle I calculated for you is, theta tilde is 120 degrees. So from here, you can get theta tilde 120 degrees and 120.26 degree. So you know this target line now. You can know, we can start the design now. So to have the close to poles to be here with this, still blue, with this angle, we will be satisfying the percentage overshoot thing. To make it smaller than 16, you can very easily know that whether this angle should rotate to the left or rotate to the right. I leave that to you as something to think about. So if I want my percentage overshoot to be smaller, should I rotate to the left, this angle, or to the right? Think about it after class. Now let's focus on the settling time. Let's think about the original settling time. So for this design, right? Original settling time this is going to be 4 over the real part of this root locus location over here. So it's going to be zeta omega n original. So the way to read it is you can draw the original root locus you know where to find this angle. So you can draw a line and then find the location of this and can read the real part of this to get this one. So the result is, this is about 0 here, 4 here. This is about negative 1.2 something. So it's 4, 1.205. And that equals to 3.32, right? So that's the original settling time. Our target is to reduce is to be 1/4 of this one. It's going to be 3.320 over 4. So that's about 0.83. So that's the target. Knowing this one, the important message is that the target settling time should equal to 4 over the new system's zeta omega n value. So if you know this, then you can calculate back zeta omega n tilde, what this should equal to. So effectively, you find the location of this pole. The result, that's approximately 4 times of this. So it's about 4.8. So it's about somewhere here. And then the values are, did I say 3/3 or, oh, okay. I had in my notes actually is 3 times. So it's 3 over here, but it doesn't matter. The concept is exactly the same. You will know the location of this one, all right? So now you need to think about what kind of root locus will make a closed loop pole to intersect at this point. So that means we need a 0 somewhere in our design. Let me draw it roughly, let's say here. The location of your introduced 0 should satisfy that if this is a pole, if this is a real closed loop pole, then it should satisfy this condition of 1 plus kgs tilde equal to 0, the most important equation in root locus analysis. And then the angle of the closed loop g of the g tilde s should be plus minus 180 degrees. All right, so your location of this closed loop pole should make this condition to be true. The angle of this is going to be the angle to the 0. Let's call it alpha 1. So the angle of g tilde equals alpha 1, the angle to the 0, minus the angles to the open loop poles, right? On a root locus, the angle is the angle to the open loop zeros minus the angles to the closed loop, to the open loop poles. So your angle g tilde of s, it should be alpha 1 minus, there's another, so this distance to the open loop pole, minus theta tilde, and then I have another open loop pole like this, minus the angle to these 2 remaining open loop poles. Let's call this one alpha 3, or theta 2, and then theta 3. So minus 2 minus theta 3 should equal to plus minus 180 degrees. All right? You can read many of these, right? Theta tilde we already calculated, 120.26. And then theta 2, you know the location of this one, so you can read theta 2 from the graph. Same thing, you can read theta 3 from the graph. So these can be read out from the root locus plot. Then you will know alpha. You will know the angle, and you know the pole, open loop 0 you should design. That's the concept. Any questions? So the details, you can read more in the textbook in chapter 9.3, which will tell you about the specific values of all these angles. But the concept is the same. So that's for today.